So the goal of this project is to try to better understand the fiscal impacts of climate change and their policy implications with a focus on the United States. And this is motivated by the fact that we might conceptually expect climate change to affect with public budgets in several different ways. So first of all, we might expect climate change to affect the costs of existing public programs, such as publicly provided healthcare or wildfire suppression efforts. Second, there is a number of climate change adaptation measures that will likely need to be publicly provided and thus publicly financed, such as large-scale coastal infrastructure protection projects. And third, through its effects on the macroeconomy, we would expect climate change to potentially also affect the level of government revenue that's collected for a given set of tax rates. Now, by the same token, we might also expect climate policy to interact with public budgets in several ways. So first, we might expect certain policy instruments, such as carbon pricing instruments, to have the potential to directly raise revenues, such as from a carbon tax. At the same time, to the extent that climate policy increases energy costs or shrinks the size of certain sectors, it may also decrease revenue collected, ceteris paribus. And finally, by reducing climate change severity, climate policy may also affect public budgets, again, through altering the fiscal costs of climate change itself. Now, the central goal of this project is to attempt to integrate each of these different mechanisms into an otherwise standard climate macroeconomic framework to think about their quantitative and qualitative relevance to climate policy design. And so the first part of the paper and the talk, the central contribution, is to attempt to construct from the bottom up an aggregate cost estimate for the public expenditure impacts of climate change. That's based on the synthesization of empirical estimates from the literature, as well as original empirical estimates of the public healthcare cost impacts of changes in the future distribution of extreme heat, cold, and wildfire events for the United States. I then, in the second part of the paper, build a macroeconomic climate economy model with fiscal impacts that allows for a rich set of ways in which climate change can affect the economy. So standard ways of modeling the climate and the macroeconomy usually summarize all climate change impacts as just a TFP loss. But in my framework, I'm going to distinguish the different mechanisms, including climate change impacts on aggregate production, on the capital depreciation rate, on government expenditure requirements, on government transfer obligations to households, on the publicly financed adaptation, and climate change impacts that affect household well-being, but not the economy. I'm going to use this framework to think both about theoretically the policy implications of climate change fiscal impacts and to quantify the welfare and policy relevance of these channels for the US economy. And so to briefly preview the main results. So first, the results suggest that fiscal costs are quantitatively significant. And in particular, the benchmark estimates right now suggest that at 2.5-degree warming by mid-century, US overall government expenditure obligations will increase by about 2%, and transfer obligations will increase by at least 1/3%. And I should say this is the sum total of local and state and federal US government consumption expenditure. The majority of this increase is driven by increases in healthcare costs, about 3/4. Now, from a public finance perspective, a 2% increase may not seem that large, but I think relative to our previous understanding of the economic significance of climate change for the United States, this constitutes a substantial increase. So prior estimates, both from the more macro and micro perspective, have found US climate change impacts of around 1–1.5% of GDP. These prior estimates disregard fiscal costs, and so adding fiscal costs significantly increases our estimate of the economic consequences of climate change for the US economy. Qualitatively, through the lens of my model, I also find that the social cost of carbon must account for fiscal impacts. And this is true not just for climate change impacts on government consumption requirements, but even for climate change implications for government transfer payment obligations. So for example, if increased hurricane activity necessitates increases in unemployment insurance payments to households because of increased local labor market disruptions, these impacts also ought to be reflected in the social cost of carbon if revenues to pay for them are raised with distortionary taxes. And this is not simply because of the marginal deadweight loss of raising the revenues, but also because these changes in transfers more formally change the set of allocations that can be decentralized as a competitive equilibrium by the planet. So in order to account for this, the social cost of carbon really should be considering fiscal impacts. And then finally, quantitatively, for the US economy, the model results suggest that these effects are quite large. So I estimate in the model an elasticity of the social cost of carbon emissions with respect to government consumption impacts of climate change of about 20, and an elasticity of the social cost of carbon with respect to government transfer impacts of about 10. Finally, the results indicate that more broadly accounting for interactions between climate policy, climate change, and fiscal policy significantly increases the projected welfare benefits of US climate policy. So even from an America first perspective, if you will, of disregarding the rest of the world and thinking only about the impacts of US climate policy for the US economy, I find that the projected domestic welfare benefits of carbon pricing increase by 20 to 300% if fiscal interactions are accounted for. Again, all of which is to suggest that these fiscal interactions are quantitatively potentially quite relevant. So I think in the interest of time, I will skip the literature review. And then for the rest of my time, focus first on the empirical quantification of projected potential climate change impacts on existing government program costs, then give a brief overview of the model, its quantification, and then present the numerical results. So one of the first goals of this project is to attempt to construct an aggregate damage function for climate change fiscal impacts. I take advantage of a number of empirical or quantitative analyses that have been done to quantify a number of these impact channels. So there's prior work by the US Department of Agriculture projecting the impacts of climate change on the costs of US crop insurance subsidies. So in the US, the government subsidizes the majority of premiums that farmers pay for agricultural insurance, and the cost of this program is due to increase of climate change. There's also estimates by the US Forest Service of the potential increase in the cost of providing wildfire suppression in the United States as the climate changes. The US Congressional Budget Office has also constructed estimates of how much the cost of disaster relief spending in the aftermath of hurricanes may change as a result of a change in climate. There's also some estimates on the effects on federal healthcare expenditures associated with general changes in air quality associated with warming. So as a result of increased temperatures and increased atmospheric humidity, atmospheric ventilation and general air quality is projected to change across the United States with associated healthcare impacts. I also take advantage of EPA estimates of projected impacts of climate change on the costs of urban drainage infrastructure across 100 cities in the United States, estimates from Moore et al. Of climate change impacts on the cost of the Endangered Species Act, so expenditures that the US government makes to protect species that are listed as endangered. And finally, I build on previous estimates of Tatiana Derigina of the impacts of hurricanes on both government transfer payments and government healthcare expenditures to infer associated increases under a changing climate. Now, one thing that became clear from looking at these channels is that healthcare impacts stand out as the largest from this set. So I then supplement these estimates with empirical estimates of a plausible order of magnitude of the impacts of changes in the distribution of extreme heat, cold, and wildfire events on healthcare expenditures. So what I'm going to show, I'm going to look at an outcome variable as total public health expenditures per capita at the US county year level. So this includes public programs both at the state and federal level, Medicare, Medicaid, children's health insurance, military, all these public health insurance programs. And in order to quantify the impacts of both extreme heat events and think about the future under changed climate, I build on methodologies developed by the Climate Impact Lab and by Max Aufhammer and what he calls climate adaptive response estimation. And so the idea behind this is that we look retrospectively how an extreme weather event, such as a very hot day, affected public healthcare expenditures in the past. And then in order to extrapolate forward into the future, we want to account for the fact that as the world warms, we adapt to that warming to some extent. So the effect of a very hot day today is going to be presumably bigger than the effect of a very hot day in the future that is generally hotter. And so in order to project adaptation to a changing climate, we allow the effect of a very hot day today to be a function of what baseline temperatures in any given county today are already, so that the effect of a very hot day is allowed to differ in a place like North Dakota, which is not used to having very hot days, versus in Texas, where there's a lot of hot days already. So we more formally allow the marginal impact of a change in D, this is, for example, the number of hot days in a given county in a given year, to be a function of the average number of very hot days in a given county already. And then when we project into the future, what is going to be the impact of a hot day in, say, North Dakota in 2050, we will take into account how already we have seen counties adapt to heat in retrospective analysis. I further control for county fixed effects, for year fixed effects, for state-specific public health expenditure trends, and for a host of demographic and other climatic control variables such as precipitation, hurricanes, other weather events that are relevant, demographics, growth, etc. So the results suggest that in areas that are not currently used to having very hot weather, the effect of even just one more extra hot day per year on public healthcare expenditures is quite substantial. So up to a 0.5% increase in annual total public medical expenditures are associated with having just one more hot day here defined as a day where average temperatures are above 32 degrees Celsius. And the results suggest that in southern parts of the United States that are quite used to dealing with hot weather, there's essentially no impact of hot weather on public healthcare expenditures. But as we go further north to areas that are less adapted to the heat, the results suggest up to a 0.5% increase in annual healthcare expenditures associated with even just one more hot day. We can define a hot day in different ways. We can look at average temperature. One could also go by the maximum temperature. And so this graph shows analogous results for defining a hot day as a day where maximum temperature exceeds 35 Celsius, where again, areas that are not used to having those kind of temperatures are predicted to see an increase in healthcare costs, whereas parts of the country that are very used to it, they fail to detect statistically a significant impact.
Lint, let me ask you a quick question here. Is it correct to interpret those results as pointing to the direction that these changes will be kind of a one-shot for these regions to adapt to this new situation, or do you expect to have, more like on a permanent basis?
I'm sorry, could you, I'm not sure I understand
the problem is that, the thing is that your approach will make, you'll differentiate an increase of temperature in Texas in the northern of the country, right? Mm-hmm. And my question is, should we interpret this as a one-shot increase in public expenditure so these regions become more adapted to this new situation? Or this will be something that you will observe more frequent in terms of the increase in expenditures, like on a yearly basis.
So thank you for giving me an opportunity to clarify that. In the model, every year public expenditure is going to be affected by the change in the distribution of heat events. And it's just the marginal damages from another hot day that are going to evolve as the climate evolves in that area. But there's the potential every year for there to be an increase relative to a world with no climate change as long as temperatures remain higher than pre-industrial levels. I hope I understood the question correctly. Does that answer the,
Yeah.
Okay.
Yeah, thank you.
So for completeness, statistically, the impact estimates for extreme cold days are not consistently precisely estimated, so I would take those with a grain of salt, but taking them at face values, the results tentatively also suggest that there may be increases in public health expenditures associated with cold or freezing days in areas that are not used to having freezing weather. So here we see in the southern parts of the United States that are not used to dealing with freezing weather, there are predicted to be significant increases in some specifications in healthcare costs associated with freezing weather events. And I think we saw this, arguably anecdotally in Texas, for example, this spring, there was a freezing weather event, and it caused a lot of deaths and significant impacts because electricity systems collapsed, clean water distribution collapsed. These kind of areas are not used to dealing with freezing weather events. Now, in order to go from these retrospective impact estimates to projected climate change impacts, we need, first of all, predictions for how global warming will map into, in each county, changes in the distribution of heat and cold weather events. And I use such predictions from Rasmussen et al., where, I'm going to focus on just a median across different climate model predictions in my presentation today. For wildfire activity, I collect estimates from the literature how each US state is predicted to see changes in wildfire activity as a result of global warming. So in this table, we see this is the average across different studies of the predicted percent change in wildfire activity per degree warming. And this ranges from, 70% increase in Washington state to over 200% increase in Arizona. This is looking only at the most wildfire sensitive states, I should say. So, to give a sense also what these predicted increases look like for warming, this is a graph using just data from Rasmussen et al. Of the predicted change in the number of hot days per year in a high emissions, high warming scenario by mid-century. So if we define a hot day as one with maximum temperatures exceeding 35 C, in some parts of the country, there's predicted to be up to 88 extra hot days per year as a result of a high emission scenario by mid-century. If we now combine this predicted increase in the frequency of hot days with the estimates of how the marginal effects of a hot day decline as areas get used to them, we see here the predicted marginal cost of a hot day on public health care expenditures by mid-century in a high emission scenario. And so comparing this graph to this graph, we see a predicted quite large extent of adaptation, so a decline in the marginal effect of another hot day on public health care expenditures. Nonetheless, combining these different estimates, the results imply a substantial increase in total public health care expenditures due to solely changes in the distribution of extreme heat events by mid-century under a high emission scenario, reaching up to a 0.5% increase in annual medical expenditures. So to the question before, every year healthcare expenditures will be 0.5% higher at this point in time.
Cinta, I have a follow-up question from Juliano, because I think part of the reason I'm also wondering whether it's annual or maybe there is a one year that you have a high cost and then it decreases. I'm thinking of the private decisions as well. Suppose that people got air conditioning in the north in the same rate as they adopt in the south. So if they are taking this decision privately and they have in their homes, so I'm assuming that the heat wave that was affecting them in one year will not be affecting them as much in the following year. So you had the cost to adapt, but then you don't have to face the same consequence in the following year. So you are abstracting from this private decision. You're just looking at the government expenditures.
Well, so if I may address this in two parts, because I think one question is what are the implications of what you're saying for the public healthcare expenditures, and the other question is what about the private costs. And so in terms of the implications for public expenditures, the model does predict. So here's the change in public healthcare cost impacts by mid-century versus by late century. And you see this part of the country, which had the biggest impact by mid-century, is assumed to adapt because people buy air conditioning and construction activity moves to night, all the things you might expect to happen. So the impacts go to zero by end of century. So it's neither a one-time nor a constant increase in public healthcare expenditures. It's an evolving effect that when temperature change is relatively new, we see it, but then as time passes, as these areas get used to hotter temperature in these latitudes, for example, before there was a substantial impact, and then it goes to zero as these areas adapt. Whereas by end of century, it's projected to be only the northernmost areas which have not yet adapted air conditioning, et cetera, to the same extent where we see any effect. So it's a time varying shift. As for the question of private costs. So in the model, I'm going to take prior estimates of aggregate climate damage functions and give them to the private sector here. So to the extent that these costs are reflected in standard damage functions, they will be captured. To the effect that they are not, they are absent, basically.
On that particular thing, which answered my previous concern, would it be possible to consider a 10 years interval instead of these two big periods? I think this would make interpretation and presentation probably easier to understand this change in the marginal pressure on the public budgets and so on.
Oh, yes. So apologies that I was unclear. My model interval is going to be 10 years. These graphs just show a 20-year period because the climate is a 20-year average, but the model is going to be a decadal interval. Yes, absolutely. Thanks. All right. So then for freezing impacts, again, if we take those estimates, it's projected to be a small band where there might be some benefit from global warming decreasing the frequency of freezing weather events. There's not projected to be a benefit in northern areas where freezing weather has no impact. There's not predicted to be a benefit in southern areas that already don't have freezing weather, but in North Texas and Virginia and some of the places where there might be a cost right now from freezing weather events, there's a modest potential benefit from reduction in the number of freezing days as well. For wildfires, I focus on the westernmost states that are the most vulnerable to wildfires, where again, we see up to 0.5% per year increase in public healthcare expenditures associated with 2.5-degree warming. So then when we put all of these estimates together, the projected total government consumption impact of 2.5-degree warming by 2050 is predicted to be about 2% increase, and about 1/3% increase in transfer payments, specifically income support in the aftermath of hurricanes. The majority of this comes from increases in predicted healthcare costs associated with hurricane, extreme heat, and wildfire events. All right, now the graphs I've shown were all sort of for one predicted point in time under one emission scenarios, but I developed a damage function that predicts aggregate impacts as a function of global mean surface temperature change. So in the background there is a linear downscaling county to global temperature model and some other things, but I'm not going to assume an RCP 8.5 scenario going forward, but rather specify a damage function that shows us as a function of global mean surface temperature change, the predicted % increase in aggregate consumption expenditure due to global warming. And this function shifts upward over time as the predicted share of healthcare in both GDP and government expenditure changes due to predicted aging of the population, as well as generally slower productivity growth in healthcare relative to other sectors. So before moving on, some caveats beyond the discussion we've already had that I need to state. So these estimates make a lot of simplifying assumptions. They hold current government programs sort of constant at their level of provision, which obviously may or may not actually occur in reality. Obviously, I also focus on a limited set of impact channels, and that is likely estimating my biasing my estimates downward, but not necessarily. So for example, I have not considered the potential fiscal savings associated with premature mortality and social program participation. And then finally, one thing that's currently in progress is that I haven't given confidence intervals or any quantification of the uncertainty surrounding these estimates, so that's something that's in progress. And so now I'd like to briefly give an overview of the model that I use to then think about welfare and policy. So I build on standard macroclimate economic models, such as Bill Nordhaus's work, the DICE model, and Gall-Salvador's work. And the two additions are, on the one hand, a very simple representation of fiscal policy. So we're going to account for endogenous labor supply, savings decisions, government consumption, government transfers, labor income taxes, capital income taxes, energy sector taxes, carbon taxes, and government bonds. And then I'm also going to allow for a richer set of climate change impact channels than is standard, again, because it becomes relevant here for fiscal effects. So climate change can affect aggregate production. That's going to be to capture impacts in agriculture and, like we said, other private market costs. Climate change may affect utility directly. This is to capture impacts that don't affect production but still affect welfare, such as losses of national parks. Climate change may affect the capital depreciation rate, specifically through the effects of sea level rise. Climate change may affect government consumption, government transfers, and may also induce publicly provided adaptation. So my economy has an infinite lived representative household with well-behaved preferences over consumption, labor, and again, global mean atmospheric surface temperature change T. And this is to capture non-production impacts, which I'm going to assume is additively separate from preferences over consumption and labor supply. The household receives income from the following sources. So the household receives after-tax labor income, after-tax capital income, where the tax is net of depreciation, and the depreciation rate depends on both sea level rise and publicly provided adaptation against sea level rise. The household also receives bond repayments from the government, profits from the energy sector, and may receive transfers from the government, which are also a function of global temperature change too. There's two production sectors. There's a final good production sector, where there's a constant return to scale technology that produces output using capital, labor, and energy inputs, and where some fraction of output may be lost due to climate change, again, parameterized by T, mean surface temperature change. The energy sector produces both clean and fossil-based energy goods, both from capital and labor inputs, and producing energy from clean sources comes at an additional cost above and beyond the cost of producing energy from fossil resources. The government's tasks are as follows. So the government has to raise revenues to finance a stream of household transfer payments, a stream of government consumption requirements. It has to service its debt, and if desired, it may want to raise revenues to finance public adaptation against sea level rise. The government can raise revenues from several tax instruments, including labor income taxes, capital income taxes, excise taxes on all energy inputs, excise taxes on carbon emissions, and by issuing bonds. And a central concept in the qualitative results that I just want to define is the marginal cost of public funds, which is going to be the welfare cost of raising an extra dollar of government revenue. So it is standard climate economy models that's implicitly assumed to be equal to 1. But here, if revenues are raised with distortionary tax instruments, it's going to be greater than 1. So there's two climate outcomes that the model keeps track of. One is temperature change, and the other is sea level rise. Temperature change at any time t is going to be a function of the history of both US and rest of the world greenhouse gas emissions. And I'm going to assume that rest of the world emissions may respond to US emissions changes with some elasticity epsilon. So if, for example, global agreement to climate policy is more likely if the United States takes a leadership role, this epsilon might be positive. Or if, there's technology spillovers in the background that if the US reduces its emissions, induces more abatement in the rest of the world, epsilon might be positive. If we're in a purely strategic setting where the more the US abates, in Nash equilibrium, other countries reduce their emissions less, epsilon might also be negative and epsilon could be 0. So I think one could make a case for a variety of values, but I take a reduced form approach to these international feedback effects by just having an elasticity and considering different values in my analysis. I'm going to model sea level rise in line with the semi-empirical model of Ramsdorff as a function of the history of temperature change at each point in time. And so within this framework, it's straightforward to show that the social cost of carbon in any period greater than 0 is implicitly defined by the present discounted value of the different climate change impacts. We're just internalizing the different effects. But what I would like to highlight is the role of both the fiscal setting and fiscal impacts in affecting the social cost of carbon. So in standard models, again, Dice or Galsov et al., we're most used to seeing just the first line, where the social cost of carbon is the present discounted value of future output losses due to sea level rise. Now here we add the present discounted value of utility losses. So this is non-market effects, again, national parks, damages, for example, of climate change, but we discount that by the marginal cost of public funds. So if we're in a setting where revenues are raised with distortionary taxes, this is greater than 1, say maybe 1.3, and that means we internalize utility impacts less than fully. So this is actually a well-known result from the literature on interactions between fiscal and environmental policy, and it occurs also in my setting. I then, more relevant to the question at hand, find that government consumption impacts of climate change ought to be internalized fully along with output losses. And if the marginal cost of public funds exceeds unity, we also ought to add to the social cost of carbon the present discounted value of the social costs of government transfer payment impacts of climate change and the associated effects on household offer curves.
10 minutes, Lint, just for you to know.
Thank you.
Lint, just one question about the utility impact. So if you were to allow for some interactions between, because you're assuming it's separable, the utility is separable in changes in temperature, right? So if we were allowed to labor supply to also respond to changes in temperature, or the utility of consumption to also depend on temperature changes, would that make this this effect larger or smaller? What is the intuition here?
No, that's an excellent question, and theoretically we know which way it would go from prior literature. So if it turns out that warming decreases labor supply, or decreases the disutility from labor, that would add another term to the social cost of carbon. So that would increase it. If climate change increases the marginal utility of consumption relative to leisure, then we want to decrease the social cost of carbon. If I hope I'm saying that right, but there is a clear theoretical prediction, basically, where if climate change, basically, if it further shifts in labor supply, that would add a separate term to the social cost of carbon, because then climate change exacerbates the welfare losses from pre-existing tax distortions, right? We already don't have as much labor supply as we want, and then if climate change makes that worse, that's a separate, in this framework, externality basically in and of itself. And so we have the new work, right? There's more and more papers that have looked at this and have found negative labor supply impacts. So it's been on my list for things I would love to investigate or quantify is the additional impacts. Yeah, that's something I could actually do in this framework because we have good estimates for the US. That's an excellent point. All right. So then the calibration, in the interest of time, I only have a brief overview. So the most interesting elements in the quantification are other climate impact channels beyond the ones I've already discussed. So for general production impacts, I consider two cases. One is the Nordhaus estimates in the Rice model, for which I separate out actual production versus non-market impacts of about 0.5% of GDP loss at 2.5 degrees, or from Shang et al. Empirical estimates of about 1.6% loss at 2.5 degrees C. For capital appreciation, I focus on the effects of sea level rise and storm surge increases, where I quantify the effects based on the U.S. Environmental Protection Agency's coastal property model. So this is a model that's spatially differentiated of coastal areas across the United States that has properties and local detail of sea level rise and geological movements relative to sea level rise, hurricane forecasts. And I basically match with my very simple aggregate model the output from that detailed model and quantify capital depreciation impact of about a 0.02% capital loss per centimeter sea level rise. And then for utility impacts, I use essentially estimates underlying the Rice model. And one thing that's in progress is I've been exploring adding rest of the world damages to make my planner not an America First planner. So that's in progress. All right, the rest of the calibration is quite standard. I match a lot of things from the Rice model or moments in the data. For my fiscal baseline, I use estimates on government expenditure from the National Income and Product Accounts, Congressional Budget Office, et cetera, et cetera. And I think the only sort of slightly non-standard parameters worth highlighting, I assume a Fiscal elasticity of labor supply of 1.83. And then as a baseline for this rest of the world response elasticity to US mitigation, the benchmark results that I'll show you assume 0.3. So if the US reduces emissions by 1%, the model, the benchmark assumes the rest of the world also reduces emissions by 1/3%. So with this the first question that I wanted to get at just, is this big potatoes or small potatoes? Is this even something that we plausibly need to worry about? And so in this graph, we have the undiscounted decadal totals of just expenditure impacts of climate change from government consumption increases, transfer increases, and coastal protection measures. And they range from about 300 billion in the 2020s to 1.3 trillion by mid-century. So this is arguably a non-trivial increase in government expenditure requirements from warming in the US.
Are these figures for the whole decade or year, or for each year in that decade?
The whole decade.
Yeah.
Yeah. So right now about 30 billion a year. So and I think, that may look smaller than one might expect, but I think popular discussions or sort of policy discussions often report total losses from hurricanes right now, which are in the billions every year. But this is the marginal effect of warming in a given year on those climate sensitive expenditures. So it's a slightly different measure than I think the numbers we sometimes see in other contexts. So in order to think about the welfare and optimal policy implications of all this, I consider 4 fiscal scenarios crossed with 2 climate policy scenarios. So I'm going to compare the welfare benefits of adding climate policy across 4 different fiscal scenarios. One is a lump sum scenario. This is a hypothetical where there's no labor income taxes, no capital income taxes, which also represents the implicit standard in climate economy models that we're used to working with. I'm going to then consider an optimized distortionary tax scenario that's sort of a theoretically efficient tax system where the government can freely optimize distortionary taxes. And then I'm going to consider 2 more realistic fiscal business as usual scenarios where either the total wedge on capital or the total wedge on labor and consumption is held fixed at business as usual levels, and the government can vary either capital or labor consumption wedges to raise additional revenues. I'm going to cross these scenarios with one scenario without carbon or energy taxation for the rest of the 21st century, and then one where carbon and energy taxes are fully optimized. And so the results are as follows. So first, if we're in this hypothetical lump sum taxation scenario where there's no distortionary taxes, I'm going to compare this line, which has no carbon or energy taxes, with this line, which has optimized carbon and energy taxes. So here, there's no need for distortionary taxes. There's no labor tax. There's no capital tax. The marginal cost of public funds is 1. The optimal carbon tax, again, America first here, is about $34 per ton carbon. The welfare gains of this policy are about $342 billion. Now, if we move to a scenario that has distortionary taxes, but they are fully efficient, at least, that would be a labor tax of about 40%, a capital income tax on average of about 5%. It's a fairly modest marginal cost of public funds, only about 1.1. And the optimal carbon tax here is lower than in the benchmark, again, because we're now dividing by the marginal cost of public funds and valuing non-market damages, among other reasons. Nonetheless, while the optimal tax is lower, the welfare benefits of having that policy are substantially higher than in the benchmark setting. And intuitively, this is because accounting for tax interactions shifts both the marginal benefit and the marginal cost curve of climate policy, but there's a substantial increase in the welfare benefits. Now, if we move to a more realistic fiscal business as usual policy scenario, here one where we hold labor income taxes fixed and raise additional revenues from taxes that fall on capital, we have a labor income tax of 35%, a capital income tax of about 35%, a high marginal cost of public funds, right, one about 1.5. Optimal carbon price is yet again lower, but the welfare importance of having it is 3 times higher than in the benchmark. So the welfare gains of having climate policy rise from 300 billion to over $1 trillion in this more realistic benchmark fiscal setting. And then finally, we can consider a setting where we hold capital taxes fixed, we raise additional revenues from labor taxes, that has a low marginal cost of public funds in my model, but yet again, the welfare benefits of this are substantially higher than in the benchmark scenario that's implicitly assumed in standard integrated assessment models. All right.
Can you explain the intuition why the third case is like generating so much more welfare gains? Is it because there's no distortionary effect on the capital taxes? Is there something to do with that or not?
So it's a few things. It's basically the fact that the government now, both the revenue benefits of the carbon tax and the avoided fiscal costs of not having more climate damages are valued much more highly than in the baseline. So the value that the government attaches to either getting $1 of revenue or avoiding $1 in extra healthcare expenditures in the benchmark is $1, and here is $1.50. Right, so the value both of the revenue raised and the climate damages avoided is substantially higher in this setting. Thank you, great question. I should have explained that. Now, as I mentioned before, there's large uncertainty surrounding my exact point estimates of fiscal impacts. So I look at the effects on the US social cost of carbon, this is the domestic social cost of carbon, of a range of what the different, impacts on expenditures of warming might look like. And so the blue line here is as a function of the predicted % increase in government consumption per degree warming, the change in the domestic social cost of carbon. And this elasticity is constant at around 20. So for each 1% increase in government consumption per degree warming, the social cost of carbon increases by about 20%. Conversely, for government transfer impacts, each 1% increase in spending per degree warming increases the social cost of carbon in the US by about 10. So with that, to summarize, again, the motivation for this work is to try to better understand the fiscal costs that climate change may have and its policy implications. The results suggest that fiscal costs are non-trivial and may increase the social cost of carbon as well as the welfare gains of US climate policy substantially, even from a strictly domestic perspective. As I mentioned, the estimates do not yet account for uncertainty, but what I take away from this personally is that, hopefully I've made a case that is a sort of a plausible order of magnitude exercise. This may be worthwhile of further both empirical and integrated assessment modeling consideration. And I thank you both so much for your questions and comments. Thanks.
Thank you, Lint. Does anyone have a question for Lint? If not, I'll have my own question.
I have just one quick
Go ahead,
question.
Edson.
So if you have, so you said like the majority of this effects are coming through the healthcare costs. So I guess like if you were to, of course you are not extrapolating, but if you were to extrapolate for other countries where there is a reliance on, the publicly funded healthcare, or universal coverage or something like that. So you expect like to be a similar, at least the weight of the, the distribution of costs would be similar across, like Brazil, for example, has universal coverage as well, or it's more than the US actually. So in that sense, you would think that would be much larger, that share is like already 75%. This could be like 90% or something, like, or close to 100.
I think it would not only be larger, but I also think its welfare relevance in general equilibrium would be higher because many other countries have a much harder time raising revenues than the US, right? So the marginal cost of raising public funds in Brazil is presumably higher than in the US. We know in Europe it's higher. We know in a lot of emerging market economies where there's still a big gray market that money can flee into, the welfare costs of raising revenues are higher. So not only would the % impact be higher, but the general equilibrium importance of it would be higher.
Right. Considering this relevance of the healthcare implications of climate change, do you expect that migration could play a role here in mitigating part of these impacts?
Yes, absolutely. And I think, yeah. I mean, so one of the simplifying assumptions that I make is I implicitly hold constant the fraction of, say, national health expenditures in every county right now is assumed to be the same in the future as it is today. So on the one hand, to the extent that right now sorting already affects some of the cross-sectional relationship we see in differences in vulnerability to heat across different places, there's an assumption that that sorting will continue, but the model is not accounting for changes in the level of population in different areas. Now, that's going to reduce damages from healthcare, I think, but I'm also not accounting for international migration and some of the border conflict and public costs that may bring. So I think omitting migration might underestimate the bias could go either way, I think.
Right. Paulo put a question in the chat, which is related to this mobility thing. And Paulo, do you want to complement something?
Mm-hmm.
No. All right. Thank you so much, Lint.
Thank you.
Great paper.
Great questions.
Edson, thank you for joining us here. It's great to see you again. See you here. Zoom is yours. You are on mute, Edson.
Can you see my screen? Okay. All right. Thanks, Juliano, for inviting for this session, and it's great to be here with you all. So this is a paper called Regulation-Induced Adaptation. It's joint work with Antonio Bento from USC, Noah Miller, also from USC, and Marine Mukherjee from Zayed University. The motivation for this paper came from the idea that many government institutions, policies, and regulations have been established to act as a buffer for shocks in general in several contexts, like employment, health, and housing. Think about if you are unemployed, the government has unemployment insurance programs that would give you some liquidity relief in times of unemployment. And with climate change, some of these research has shown that some of these shocks may become more frequent or more severe. So we were, wondering whether it was clear a priori whether these policies would induce or constrain private incentives for climate adaptation. So you can think, on the one hand, it might distort private decisions. That way would inhibit adaptation. On the other hand, it might correct market failures. If that's the case, it might induce adaptation. Given that, there's a lot of political gridlock surrounding climate policy nowadays, understanding how these policies would potentially provide incentives for adaptation is very important. Now, from the get-go, I want to make sure that we understand this as potential complements, not substitutes of first-best climate policy. What we do in this paper is develop an analytical framework to highlight how this pre-existing regulatory incentives could potentially trigger some behavioral responses that would either inducing or inhibiting climate adaptation. We will estimate some key parameters to calculate some simplified welfare effects of what we call regulation-induced adaptation, which is a co-benefit, and in our context, a co-benefit of the air quality standards for ambient ozone. And we studied this because we think it's an ideal context. We are looking at the impact of temperature changes on ambient ozone concentrations in the US. We have data from a long time horizon, 1980 to 2013. The reason why we chose ozone is actually a pollutant that is formed, not emitted, and it depends on sunlight and heat. Therefore, it will be affected by climate change. And also it's because it's a negative pollution externality, we get that the Clean Air Act is regulating ozone as well. So our results, 1 second, Mike, preciso, silêncio, silêncio. The preview of the findings, our results show that or demonstrate that these existing policies that are unrelated, or at least they were established in a way that was unrelated to climate change, they might, facilitate adaptation, and the magnitude is actually of economic significance. Just to give some numbers, some preview of the results here, adaptation in counties in no attainment with the national ambient air quality standards would reduce the impact of a 1 degree Celsius warming on ambient ozone by 0.64 parts per billion. That's how we measure ozone, or about 1/3 of the total impact. And half of this effect is actually due to the regulation-induced adaptation, okay? If you were to look at these, take these numbers at face value and use the marginal damages of a 1 part per billion increase in ambient ozone that we took from other papers and the warming scenarios RCP 4.5 or 8.5, this would translate into $800 or $900 million per year in total welfare benefits by mid-century. 400 to 470 million would be attributable to the regulation-induced adaptation, which, as I said, is a co-benefit of the national ambient air quality standards for ambient ozone. Just for comparison, in 2015, when EPA was evaluating whether they would make the standard more stringent, they calculated that the cost of reducing the national ambient air quality standards for ozone threshold by 1 part per billion would be about 300 million, slightly below $300 million per year. So you can see that these effects are actually quite important. Now, we think this paper contributes in 3 ways. First, it provides this analytical framework, incredible empirical evidence that these non-climate policies, or at least policies that were established for reasons unrelated to climate change, but these policies are correcting some market failures. They not only smooth out some shocks, but also induce adaptation. And it's important to compare what the literature was showing before this. Prior research had highlighted the perverse adaptation incentives. They were basically looking at how existing policies were distorting private behavior, and if this is exacerbated by climate change, they would distort even more. So, for example, an in Sri Lanka showed that farmers would potentially not change their crop choices because if they had losses due to climate change, they would potentially be covered by the federal crop insurance program. Also, Tatiana, these are papers that Lint also mentioned in her presentation. Tatiana also provide evidence that when there is a hurricane, so non-disaster related government transfers, for example, unemployment insurance benefits, they would potentially lead people to not leave the area as much as they would have if they didn't have any liquidity relief. So in that sense, like, you're distorting the decision that could potentially be a way to adapt to climate change. Now, also, the work demonstrates that existing governments can also provide a catalyst for adaptation. So other papers, other work had shown, the role of market forces or private responses. For example, Baraka looks at the diffusion of air conditioning. Tatiana and David Molitor look at how people could migrate from the areas that are hit by hurricanes, for example. But private incentives may be limited in scope or distribution. And third, it points out a non-trivial incidental co-benefit of the Clean Air Act. Prior literature has examined the impact of the Clean Air Act on air quality itself or other economic outcomes, also providing some unintended consequences. For example, Gibson looks at how when you're regulating one side, it increases pollution in other channels. Here we are looking at the interactions between the climate change regulations and between Clean Air Act regulations and climate change, and this has been overlooked in the literature. Now, before I continue, while we are just looking at a situation here that is a negative production externality, which is the formation of ambient ozone, this type of induced adaptation may happen in other contexts, as long as the corrective policy reduces the market failure and climate change would exacerbate the market failure. So 2 other examples. Suppose, we are looking at vaccination. If climate change will increase the incidence of some diseases, for example, influenza, which has been shown in the literature, if there is an infrastructure for vaccine distribution already, that would potentially attenuate the impact of climate change because people would be inoculated with these with the vaccines, with the influenza, with the flu shots. Also, in terms of law enforcement, if there is an increase in temperature, there's a lot of studies showing that would affect the probability of somebody engaging in unlawful activity. So if there is already a well-established law enforcement agency, and if they are funded, then this could potentially reduce the severity of the incidents or deter that type of behavior, also attenuating the climate impact. So these are two examples where vaccination, there's externalities involved, the same for law enforcement. And so again, these are policies that are correcting market failures from the get-go. And if they are exacerbated by climate change, they would potentially be inducing adaptation in certain way.
Edson, may I ask, maybe you'll get to this, but conceptually, how do we think about this from the planner's perspective, sort of theoretically? If basically, I think what you're saying is that the marginal damages from climate change depend on other regulations, right? On air pollution regulation. Do you have any sense of how that changes how we think about sort of the social cost of carbon? Even what would first best policy look like here?
Yeah, so we have looked at this from the perspective of the private behavior facing the regulatory constraints. So we're not thinking, well, we could translate this into a social planner problem, I guess. But here it is as if we are not changing the constraints as of now. We're just saying within those constraints, what would happen if there is a change in potential behavioral responses due to climate change. And then if there is the constraints we are assuming that they would still work in that setting. So in that sense, like what you're asking is how we could design policies based on these behavioral responses, that we are not doing this. And we leave that as a scope for future research. Yes.
Edson, just a follow-up question on that front, which I think you're talking about the transition, the challenge about transiting to a low carbon economy or something like that, in which you're mapping the initial state. A suggestion is to take a look on how the NDCs, the National Determined Contributions, were considered in the Paris Agreement, because the framing that they had was exactly the framing that you have here. It was about identifying within each of the countries what were the policies being implemented in those countries, and then setting up the ambition compatible with those policies, which I think it's interesting in terms of framing for your contribution using Paris Agreement as an example. And another example that came to my mind are the whole set of subsidies to oil and gasoline that we find around the world that goes in the other direction.
Oh, that's true. Yes. Well, I didn't know about the framing, and so that's a good idea for us to actually.
Yeah, if you are interested, I can connect with the guys that was behind that kind of negotiation in Brazil. Very nice.
Oh, yeah, that would be very interesting, because that would be a nice way to also frame this. I'm just taking notes here. Sorry. Yeah, okay, so I'll put a note and then I will take on the offer, Juliano. All right, so just to clarify some issues of the setting that we're going to be studying, many people think of ozone as something that is good because we talk about like the ozone layer, so that's like very high and it protects us from the UVs, but like we are talking about the ground level ozone, which is a pollutant, and it could potentially create some issues for lung function, and then if people have asthma, they could have asthma attacks, and so on and so forth. And affects vegetation, affects a number of other things on the ground. And just to give you a picture, the picture from my introductory slide. So here is LA, and you can see clearly the cloud of ozone and the level of the city. Like you can see the buildings in this cloud of smog that is pretty much the ozone, the bad ozone. LA is one of the worst places in the nation when it comes to ozone. Now, how is it formed? So we emit from a number of sources on the ground, like tailpipe emissions, from smokestacks, from the heating systems in houses, emitting NOx and VOCs, and then there is a combination of NOx and VOCs that react under the presence of sunlight and warm temperatures, and that creates this ozone both on the ground and also high in the atmosphere. And the Production function, it's not exactly a Liontiev, but it looks like. So there is an optimal combination of NOx and VOCs that produces the highest, levels of ozone. So there are places that are going to be VOC limited. So if you change a little bit of the VOC emission, is going to change a lot the production of ozone. But if you change, a little bit of NOx, it's not going to change much. So on the other hand, when they're NOx limited, if you change NOx for a little bit, it's going to change ozone formation by quite a bit. So I think this is important when you talk about the framework that I will explain in a few minutes. Now, in our analytical framework, like in the paper, we develop a little more formally. And here I'm going to just give you the intuition behind it. So we are looking at the conditions under which we could expect this pre-existing policies to induce or inhibit adaptation. And the main thing here is to see this, these interactions as how the interaction would potentially make the problem worse. And so if the policy is correcting a market failure, like as I said, in the case that we are studying is going to be pollution, that would be exacerbated by climate shocks, then with the constraints that we have, they would potentially incur in extra costs to actually bring the levels of the externality under control. So like if it's, we're talking about externalities, but it could be any market failure. Now, in the case of private behavior, so if the policies are actually distorting a private behavior, as I said, one example is the farmers that are not potentially changing their crops because of the federal crop insurance program, then in that sense, like climate shocks could potentially increase or exacerbate those distortions, and it would make the problem even worse. And so it could be one of the cases in Lint's work that it would increase the fiscal consequences of that type of policy. Now, in the context that we're looking here, let me just give you a very high, broad view, a picture of what we are doing. So imagine that we have a place, let's say a county, that has ozone under control in the baseline. That's going to be this horizontal blue line, which is the threshold for established by EPA in terms of what is acceptable in terms of ozone concentration. Let's assume that we have a linear function. Of course, this is just to simplify the argument here. A linear function on an index that depends on NOx and VOCs, and then climate. All right. So this point A is what we would have here as, I'm putting a perfect complements here between NOx and VOCs. This is the point A. So basically there's a production process are emitting NOx and VOCs, and we are in this point A. For this level of emissions, if there is a change in climate, so a shocking climate, it would just make for the same level of emissions higher ozone formation. So we would go from point A to point B, just because there is climate change. Well, in this case, this county now is over the threshold, so it would be under a stringent regulation from EPA, and EPA would make pressure on them to reduce emissions of the precursors of ozone. If that is the case, they will go from point B to eventually going to point C, but the only way they can do that is by actually reducing emissions of NOx and VOCs. So at the end of the day, with the pre-existing regulatory constraints, it just makes the shocks that were coming from climate change, bring them under control if the existing regulation is still valid in that setting, which is what we are assuming here. Okay, so the idea here is that like the changes that are happening here is change in production under climate change will be emitting less than without climate change. So what we are, in the paper, as I said, we have a more elaborate framework here, but it's quite simple. So we are looking at the monetized changes in utility driven by a changing climate. And that's what we are going to be calling regulation-induced adaptation. That depends on two things: how this, externality of the pollution affects a human, so it's affecting the utility negatively, and we are going to monetize that by lambda, which is the marginal utility of income. So this is going to be the marginal changes, marginal damages, times the change in emissions under regulation or without regulation. So since we are reducing emissions, this effect that we are going to call the regulation-induced adaptation is negative. So negative, you're going to have a positive, a gain, a welfare gain, if there is this reduction in emissions of ozone precursors. We'll be estimating this portion, the portion in parentheses in our empirical analysis, and we're going to take the marginal damages from the literature, which is estimating what is the impact of what is the willingness to pay to reduce ambient ozone concentrations by 1 part per billion. And we're going to use that in our calculations later on. So in order to estimate this IRA, you have a question, Lynn?
Yeah, sorry, where I may just not have absorbed it, but the abatement, basically the cost of this adaptation, is that sort of at an optimum equal to something, or where does that come in?
Yeah, so you mean this this 5 prime, or
the cost of reducing the emissions?
Oh, I see.
The abatement technology.
Yeah, so the cost is going to be like we are assuming that they have some technology available and they will be using at the market price, and we are assuming that they're price takers from the technologies that they need to avoid emissions. So that's why at the end we are going to compare that with the costs that they incur. Yeah. Okay. So in order to estimate that regulation-induced adaptation parameter, we need some data. So here I'm just showing you the patterns in the US. Climate has changed. Temperature has risen already. It's more or less a 0.5 degrees Celsius from 1950 to now, which is basically what we are seeing in this figure. Ozone, on the other hand, since it has been regulated since the early 70s, it has decreased and decreased more in the solid line, which is for the counties under stringent regulation from EPA, and a little bit, in the counties that are not under stringent regulation, but also some pressure from EPA. Now, those counties that are in our sample and are out of attainment or out of with ozone concentrations above the threshold, they were about 70% in the beginning, and then they dropped. Counties can make changes and bring the emissions to a certain level that the ozone concentration doesn't exceed the threshold, and they were declining up to early 2000s when a new standard that was put forward in 1997 was actually implemented. And you can see here a jump in 2004 when the standard is implemented. It's a more stringent standard, and so many counties were out of attainment, but then they dropped quite gradually. So in 3 years, many of them were already in attainment. These ozone monitors are all over the country. I put different colors for where they are because they move quite a bit. We are not going to have a balanced panel in this analysis. There are some rules where they should be. They have to cover areas with certain population, and the local agency decides where they're going to be put, and EPA approves or not the location. So the blue ones are the ones that were put in place in the 1980s, the red ones in the 90s, the red triangles in the 90s, the green squares in the 2000s, and the black diamonds in the 2010s. So you can see that this is all over, but it's concentrated in places with people. So it's pretty much like in metropolitan areas all over the nation. But many counties are not monitored. They are never monitored, okay? Here are the counties that are in no attainment. So in the 80s, which are the dark red in this case, you can see that many of the metropolitan areas were out of attainment. And then in the 90s, some of them are coming in no attainment as well, the orange ones. And then in the 2000s, the yellow ones, and the 2010s, the mustard ones. And the blue ones are the counties that are always in attainment. They had been monitored, but their levels of ozone are lower than the threshold. And these areas in the countries that are gray are areas that we don't have any reading. Like it's not monitored, and we cannot say much. So they're not gonna be part of our analysis. To estimate that that parameter, the regulation-induced adaptation, we build on previous work where we are unifying 2 strands of the literature, trying to estimate what is the effect of weather and climate in the same equation. Basically, the idea here is that we can decompose the meteorological variables, like let's say temperature, into 2 parts. One that we call climate norm, and we operationalize that by a 30-year moving average. And we are assuming that this would capture the long-run effect of climate And if it's the long run, it's because you have given time for the economic agents to observe what's going on and also to adjust their production processes. And the shock, which is a deviation from those climate norms, and this would be reflecting the short-run effect of weather, and this would be not incorporating adaptation, or it would be very limited because it's just on a daily basis. And we are going to have some robustness checks looking at whether they would respond in a very short period of time. Adaptation in this context is just the difference between the response to the changes in climate norm versus changes in the weather, or in the shocks. And we can, because we are estimating these two parameters in the same equation, we can just take the difference and test the significance of this adaptation measure. And because it's also the same economic agents responding to weather shocks or changes in climate norm, we can see we don't have to make extrapolations over time or over space in order to understand what's going on in terms of adaptation. So this is the method in a very, very short summary. The idea here is that we can...
Just a question
sure.
on the method. How concerned are you about endogeneity on those measures on ozone?
So these are not for ozone, right? Like these are just measures of meteorological conditions. So ozone is going to be our dependent variable. So they're going to be affected by these changes in both components.
Right. So it's not an issue.
Yeah, at least as long as the firms are not responding, at a no marginal way, let's say over time in response to climate change, we would be fine in this case. Only if there is like a non-gradual change.
But the endogeneity here will be associated with areas in which the problem is more relevant, right? In a sense, and that's fine, and that's fine, right?
Yeah, and that's why like we try to bring these two components in the same equation, because we could control for location fixed effect, right? And so like if there's anything special about them, we could still get some of this at least time constant unobserved heterogeneity.
Okay, got it.
So in practice, what it boils down is, in the previous methods, let's say the panel data approach that has, very popular in the literature, we would be taking a measure of temperature, which is this dashed line over here. This is just an example from LA in 2013. And we would take the average, and then the deviations from this average would be the shocks. Right, so you can see that that's basically assuming you have to eliminate climate from the equation, because climate is something that is moving at a very, very slow motion over time. And here, what we are doing, we take this 30-year moving average, so basically looking at the 30 years prior to this month, and taking an average. Of course, like every year you update that, right? But each month is going to have one average, and then we can deviate the observed temperature from those monthly moving average. So here the source of variation are twofold. One is actually different months will have different averages, and second is like as you update this over time, the agents would observe what has happened in the past 30 years, at least if they pay attention to what has been happening in the past 30 years. We will allow them to respond to that information. So with those two components, you can see that there's variation in both. Like the top graph is looking at the climate norm component, and the bottom graph is just looking at the variation in the deviations from the norm. So we have variation in both for the empirical approach. In the empirical framework, we are just basically estimating this equation where ozone is a dependent variable, and we are interacting these two components of temperature, the weather part, which is temp W, and the climate norm part, which is temp C. And we're, being flexible and estimating for counties that are under stringent regulation. These are the no attainment counties, and counties that are under less stringent regulations. Let's call that the attainment counties. Notice that there is, they're lagged by 3 years because EPA gives at least 3 years for them to adjust if they are in no attainment. And also, notice that the way we have defined the temperature here, temperature norm is also lagged by 1 year which is we give at least 1 year for the agents to adjust. We're in the robustness checks, we give like many more years. It doesn't seem to make a huge difference, and that's why we stuck to one year here. And each observation here is a monitor reading in a particular day, T. Notice that we have some other meteorological variables in X. We are using variation within the same monitor location in the same season. So days in the same location I with monitor I over the same season. So there's like variation in the months, the monthly moving average, also variation in the days. And also we are controlling for very flexible for climate region, by season, by year, fixed effects, allowing this to change due to different policies across climate regions. There are 9 in the US, also whatever is happening in each season. So just to go over the results quickly. Here in this first table, we are showing the average effect. So this without the interaction, you can see that 1 degree Celsius increase in temperature shock or weather shock would increase ozone concentrations by 1.65 parts per billion. In the short run. In the long run, the response would be 116. The difference is basically 0.48, which is the adaptation, the average adaptation for the counties in our sample. Just to give an idea of the magnitude, every time, like in the past maybe 20 years, that EPA has updated their ozone standards, they have reduced it by 5 parts per billion, just to keep that in mind. Also keep in mind that by 2050, under RCP 4.5 is 1.4 degrees Celsius of warming, RCP 8.5, 1.6 degrees Celsius warming. So we would have to multiply these numbers by those in order to get the numbers in your head. Now, when we break down for non-attainment and attainment, you are going to see that the effects in non-attainment counties, they are dirtier in general. They have like more emissions of NOx and VOCs, so the response is higher. But so is the adaptation. They're adapting 0.64, what I had said before. And the counties under attainment, they are also adapting for other reasons. There might be other regulations, also technological improvements that are available to both attainment and non-attainment counties. One example, so if you think of solar panels, they are being installed in both counties at the same time, and they are producing electricity midday, which eliminates emissions from, let's say, other sources. And it is the time of the day that you would have like the highest ozone formation, because there's a peak of ozone formation in midday. And so you have adaptation in both, but adaptation in non-attainment counties is much larger than adaptation in, it's more than double adaptation in attainment counties. So the difference then is basically what we're calling the regulation-induced adaptation. What is the extra adaptation that you are getting due to the counties that are over the threshold set by EPA? What are the efforts that they're making to bring the emissions down so that ozone concentrations are not above the threshold? So that's 0.33 parts per billion. Now, this number is pretty stable. We have controlled for other policies on the inputs. Like, for example, California has put forward a gasoline that is just to reduce VOC emissions since 1996. So we removed that from the sample. The number is pretty similar. We also have controlled for other policies on NOx, which is the other component for ozone. There's the NOx budget program in the northeastern part of the US, the NBP program. There's the Reclaim in the South Coastal Basin, which is basically LA and surrounding areas. If you eliminate that from the sample, we find pretty much a similar, Also, if we just break that down by the distance from the threshold, you find that, most of the adaptation is coming from in places that are farther away from the threshold. So if you are within 20% of the threshold, you are getting a lower level of adaptation, but it's still there. And then if you're going from 20 to 40% of the threshold, or over 40% of the threshold, you are actually finding the regulation-induced adaptation coming from those extremes. One reason why this number is smaller is because EPA at some point, when you're recognizing that ozone is affected by meteorological conditions, they were saying, oh, if you are just above the threshold, let's call that tentative attainment. So they were under less stringent regulations, so they didn't have as much to adjust. That's why this number might be smaller in this case. We have done a number of robustness checks, changing like what is the moving average 3 to 20 years and 30 years. So if you think of measurement error, that would potentially give us some idea. It doesn't change very much. I have those tables in the appendix, in the slide appendix, if you want to see them. Also, how long you give to time to adapt. We gave 1 year, but we can give 10 years, 20 years. It doesn't seem to be relevant here. It looks like people are looking very few years in the past, kind of a myopic type of behavior. We have also put Ozone Action Day, which is basically short-term changes in behavior that local pollution agencies trigger when there is a forecasted bad ozone day. So you could imagine that you could do some you could engage in some adaptive behavior in a very short notice. That doesn't change the responses that we observe here very much. So it could happen, but we didn't see much. We are also changing the estimates based on whether we take the switchers from no attainment to attainment or vice versa, or those that stays the same throughout the period. It doesn't seem to change much. And we do monthly versus daily moving average, balanced, unbalanced, using other meteorological variables, let's say wind speed and sunlight for this small subsample that we have the information. It doesn't change the effects much. Now, taking those numbers at face value, as I said, this effect on ozone is what the literature would call the climate penalty on ozone. That would be very large, as the numbers are here in the first and second row. In the third row, it would be the savings from adaptation, which are quite large from 1 degree Celsius increase in temperature. And the regulation-induced adaptation is actually over 50% of that. Now, looking at columns 2 and 4, which is what we focus more on the paper, under these two scenarios, for 2050, mid-century, we would have savings from adaptation from about $800 to $900 million per year. And, or the regulation-induced adaptations 410 to about 470. Now, as I mentioned earlier, to compare, these are the savings from adaptation. What about the costs? Well, the cost would be about $300 million a year if you were to reduce ozone standards by 1 part per billion. So that's what EPA has estimated that you would, the economy would spend per year to bring the marginal damage of 1 part per billion down. Now, one interesting aspect of our study, and I'll finish in a few minutes, is looking at how different is the response across the nation. You can see here that in places, the third column, just to make it shorter, the third column is showing that if we split the entire nation among counties that have middle ground beliefs in climate change, basically like they are surveying the country to see whether they believe or not in climate change. So if you split the counties into three terciles and put the middle tercile as the reference, you observe that there is some adaptation there, but the low belief and high belief counties are doing more. The low belief counties is because the low belief counties in attainment, they are not doing at all. They're not doing much at all to actually respond to climate change. And the counties that are in no attainment and are high belief, they are doing more than they were required to. So you can see that, depending on your beliefs, you might actually react differently, and you might produce results that are actually heterogeneous across the country, which is an interesting thing. The other thing that we did was over time. Is it the case that you have low-hanging fruits and then suddenly you don't have the opportunities anymore? Well, it does look like that, although statistically speaking, we cannot rule out that they're the same. So over the 80s, 90s, and 2000, it looks like there are opportunities for adaptation, regulation-induced adaptation in a similar way. So just so I'll be concluding soon. So just to finalize, so we think this with this study, we have conceptualized and presented some evidence of the policy-induced adaptation. As I said, previous studies have put forward innovation and market forces as triggers for adaptive behavior, but here we are showing that government policy might foster adaptation differently from previous research that has shown the government programs to inhibit adaptation. In particular, we are looking at the next for ozone, next correct a market failure, which is a pollution externality. And so it would be, it would produce this adaptation that is an important co-benefit or, of a second best policy, if you don't have carbon pricing. We think this opens a new avenue for research. There are many other programs that are incidentally contributing to adaptation, as long as you believe that those constraints will be in place in mid-century, which is basically what Lint was referring to. Like, what if these are changed because of a social planner type of a policy? We think that that's where things are potentially going here. There are two ways to pursue this climate policy. One is the first best carbon pricing, and we are hopefully seeing some moves towards that. But if it's not the case, then one could be thinking of strengthening the policies that are already in place and just exploiting these co-benefits. And as I mentioned, there are many opportunities, for example, public infrastructure for vaccination and for other infectious disease, and also law enforcement and so on and so forth. I'll stop here. Thank you.
Thank you, Edson. It was great. It seems to me that the most surprising part of these results is the fact that we are talking about something that is much more than a theoretical possibility, right? It's a sizable impact, right? Because having the pre-existing policy framework as a lever to new changes, I think it's somehow I think in everyone's mind. But I think what you showed here is an approach in which you can measure that, and it turns out to be quite sizable, right?
Yeah. And as Lint was mentioning, so you could use these types of analysis to actually think about how to actually design changes of these policies to incorporate this potential adaptive behavior that they are triggering.
Yeah. I see the exercise more like quantifying the importance of those levers, and then you can use in terms of changing the behavior of private sector, or you can fix the public sector more, the regulation.
Yeah,
interesting.
Yeah.
More questions from the audience?
Hi there. Hi, Edson. Nice to meet you again.
Seeing you.
I actually, hearing you, I think this is a positive result. And everything we hear nowadays is negative effects and that no policy is done. So I would like just to hear you, not about the model, but really, do you read your results as good ones, as unexpected good ones, or is still too much to do? And
so I think I see it in two ways. So there are many policies that we don't give as much, we don't give the value that they should in the ways that they are actually providing us with a buffer for climate shocks. Like if you think in Brazil, even though it's there are so many issues, like for example, healthcare coverage, right? They could still be helping us in this respect. Of course, as Lint has mentioned, it could increase the fiscal constraints, but if the policies are there and they are still in place, they will actually act as a buffer. Now, there are many other policies that may be inhibiting, and then I think that's the part that we should be paying more attention. Like in the US, there's the federal crop insurance program. Like, farmers will not adjust if they know if they have crop losses, they will be compensated by the government. So in that sense, if these are the types of policies that we may be facing in the future, then we should reevaluate them. So I think I see it as more positive in the sense that there are many things that we have that we are not quantifying all the values that they potentially are providing, especially in this world of changing climate. On the other hand, it's a wake-up call for reevaluating some policies that are already creating some distortive behavior.
Thank you.
Yeah.
Thank you, Lydia. Great to see you here.
Thank you. Lint, would you add something to that? Do you have a positive, optimistic view? with
You're eager for
regulation.
good news, right? It's that
Yeah,
as
I am.
Brazilians, we are eager for good news. Good.
Well, I think I would just touch upon what Edson said is the, there's two coins of it. In my presentation, I focused on the fiscal costs, but there is a flip side that it is a shock absorber. And I think, especially once we broaden our view to think not just about efficiency, but from a distributional perspective, right? So some of these systems may disproportionately benefit more vulnerable segments of society at an aggregate cost that may be, it's an open empirical question for every one of these policies, but I think there's also the potential to not just decrease aggregate damages, but potentially also indirectly mitigate some of the equity concerns that exist through some of these other policy levers. That's probably the most optimistic spin that I could think of, but I think it's true.
Thank you.
That's awesome.
Yeah, I'm aware of the time, and I think it's great to finish these brilliant presentations, the good vibe. So thank you, Lydia, for providing us with these motivating questions. And I'd like to thank Edson and Lint for these brilliant presentations, and the audience and the organizer to promote this session. To me, I learned quite a bit. Thank you so much, guys. Take care. Stay safe.
Thanks, Anton. Thanks, Juliano. And Flavia, I didn't see you. Hi. Okay, thanks, Juliano. Yeah.
Bye-bye. Thank you, guys.
Good seeing you, Lydia.
You too.
All right, bye-bye.